Hey guys, so this is your 361 review. So let's just start by looking at Maxwell's equations. So let's see. Let me just write up here. This is P361. Okay, why is that doing that? Who knows? Review. Okay, so let's start. All right. So let's start with Maxwell's equations. Now you may not remember, and we may not have actually made it too far into Maxwell's equations, but it's a good place to sort of give you a cool lesson about fluxes and all kinds of things that we're going to use later in our problem that we're going to do. Maxwell's equations. Kind of hard to write on this thing, so excuse me for being messy. All right, so let's write the first one, and I'm going to write them in integral form. This one is one that you first saw in probably 116. It's Gauss's law, right? And it tells you that the flux through a surface, and that surface is this surface, and is just a flux of the electric field is just equal to the enclosed charge over this epsilon near 0, which is the permittivity of free space. Just recall. Okay, next one is called Faraday's law, and it's a relationship between this line integral, which is basically a potential, and a change in the magnetic flux. Okay, this is this phi b. Okay, so that's not written in an integral form, but of course you could write phi b in an integral form if you wanted to, right? Because it's just the flux through a surface, and that's just, of course, the flux through a surface of b dot dA. Okay, nothing special here, just flux. And it tells you here that basically you can get a potential by changing the flux of the magnetic field. And you should know that as Faraday's law. Okay, and now the next one, which really doesn't have a name, but people have various different names for it. One is the magnetic Gauss's law. I hate that one. I hate that name for it. Other people just call it no magnetic monopoles, and I'll explain that in a second. So I'll just write, no name or magnetic Gauss's law, or no magnetic monopoles, and I'll explain why it's called that. It's kind of a cool thing. All right, and again, this is that integral that you see over here, right? So it says that the flux through any surface of the magnetic field is 0. Okay. Now, notice here that this, and I'm going to explain this all as we go, this flux here, that doesn't mean the flux is always 0, right? It can be sorry, I better explain that a little better. This means that the total flux through a closed surface is 0, okay? So I'll put a little circle on here to mean closed surface. So it really should have put a little circle around this one too, because this circle means closed surface. But in general, this flux is not defined as only through a closed surface, right? This could be through any surface. And if it's not closed, then there's no requirement for the flux to be 0. Any surface S. Okay. All right, so this thing here says the flux through any closed surface is 0. So if we think about a surface like, some surface here that's closed. So think of a source 3D surface. Any magnetic field lines that come out of the surface, okay, better come back in at some point. Otherwise, the flux will be non-zero. Now, how does this happen? It happens because you don't have any magnetic charge. All you have is like little tiny bar magnets, right? Which have like a north and south pole. I can't ever remember this, but I believe the field goes out at the north and comes in the south. Can't remember, whatever. But you have both of these things in, so the field lengths that go out have to come back in. If you had a magnetic monopole, right? So there's our surface again, like a little charge here, little magnetic charge, like say just a North Pole, then it would be just like an electric field, and things could go out, right? And never come back in because they end at infinity somewhere. They end on a negative, a South Pole somewhere else, right? But that just can't be the case. So this is kind of why this is exactly why, sorry, this is called the no magnetic monopoles law. All right, last but not least, and we're going to spend a bunch of time on this. This says the line integral of a B field around a closed curve, okay, is equal to mu 0 I enclosed. Okay, and we're actually going to add a term to this, but I'm going to explain before we do, because this this needed to be corrected, and I'll explain why. But this one is amperes. And it kind of plays the role of Gauss's law. You know, if you remember from 116, you kind of use this to calculate B fields and say a wire, right? And you make these Amperian loops, like you might say, the way you make a Gaussian surface, right? So you might say here's a wire with carrying current I, and you might make an Amperian loop kind of around that wire, okay? And the idea is that you integrate around that loop, that closed loop, and it will be equal to mu 0 times the enclosed current, so the current that pierces the surface enclosed by that loop. So if you can think of a surface, right? This thing defines a surface, right? This loop, it bounds a surface, so the current that pierces that is the I enclosed. And you need to know the direction of the B field and stuff to use this, and just the way that you have to use the symmetry of the problem in Gauss's law, and you can't always use Gauss's law to get the field, the E field, etc. Same thing for Ampere's law. I hope you vaguely recall that. So let's take a look at that last one, because this last one is not correct the way it's written right now. Okay. All right, so let's see. Let's see why it's not correct. Let me get a new layer here. Hello? Okay, here we go. Turn this one off. All right. Okay, so let's look at, I'm going to rewrite it up here first. Let me just rewrite the equation. B dot dl is equal to mu 0, and that's the permittivity, no, permeability of free space. I can never remember what they're actually called, but that's mu 0. And this is I enclosed, right? And that's a B. Okay, so let's look at a specific example. Let's say we have a circuit, it has a little resistor, has a little battery, and it has a capacitor. So just think of a parallel plate capacitor here. Okay. All right, so imagine doing this integral here for a surface that just sort of enclosed this wire. Sorry, for a curve. Here we go. This is the curve, so this is C. So this is curve C, right? Curve C, right here. And you can see that the wire, right, the current that flows through this thing flows right through, and this would be I enclosed. No big deal, right? Great. And this, the surface that it pierces is the surface bounded by this loop, right? Everything's consistent and great. This would work fantastic. All right. But imagine the situation where we have the same curve. So I'm going to draw it again. I have my circuit, a little resistor, little battery, and up and around. And we have parallel plate capacitor. And now I have my curve, same curve C, even put in the same place, okay? This is C. But think about it, the surface that's bounded here is not the only surface that this thing can bound. So think of it like this. Imagine you take a sock, and I'm the worst drawer on the planet, but here is the place where you put your foot in, right? That's the place that you put your foot in. Well, this rest of the sock looks like this, right? Looks more like a boot, but you get the picture, okay? So you can see it's a sock, and so the surface is the surface of the outside of the sock. So you can imagine your foot in there, and the outside of the sock, right? Not the inside, but the outside is the surface, and it's still bounded by that curve, right? So if you think of a coffee mug, right? Coffee mug looks like this, or glass. Let's go to glass so we don't have to deal with this stupid handle. And I'm a terrible drawer. But the coffee mug has a boundary that's actually this same curve, right? So your coffee's in here, right? All nice and hot. Yeah, my attempt at drawings is pretty bad. Okay. So imagine, let's put our sock in here, except for it'll be more like a bubble that you blow with one of those big bubble makers. Okay. All right. So now our surface is this whole big bubble, and it, you know, it encloses this one plate of the capacitor. Now notice that there is no current flowing between the plates of a capacitor. I hope you know that. And so even though the battery's pumping out current here, what's happening is, I mean, until the thing is fully charged, there's current flowing down this wire and charging up the capacitor, right? But there's no current flowing across this line. So if we had a value for this integral here on this side, using curve C, it's the same curve, right? So we got whatever we got, 25, right? Whatever it was, in whatever units this is in. Then we need to get 25 here too for the same integral, but we won't because I enclosed is 0. Okay, so it makes a big problem because on this side, the integral C around that closed curve, the same exact curve, B dot dl, is 0. So there is a problem with this equation. It is incorrect. And so Maxwell fixed it. So Ampere's law was the original one, and Maxwell came along and fixed the equation. And it's, no one calls it the Ampere-Maxwell law, but that's what it is. And he fixed it to include this next term I'm going to show you. So we have this, we have mu 0 I enclosed, and then we have plus this next term, which is mu 0 epsilon naught, the change in the electric flux through that surface. So notice how this now makes sense, right? There is a flux of electric field through here, which you could easily calculate with Gauss's law. And it changes with time because the capacitor is charging, right? Obviously, if the capacitor is not charging because the battery's disconnected or it's fully charged already and it stops charging, then you don't have any current on this side over here, and you don't have any flux, and you're fine, right? But in the case where there's actually current flowing through here, right, you're going to get a change in time of the flux here. And so this is the true last Maxwell equation. Okay. All right, well, let's do an example problem that we're going to have to use a bunch of stuff from E&M, including electrostatics and electrodynamics. So again, another layer. Okay. All right, so we're going to have here a similar setup where we have a, sorry about this line, we have a current flowing in here, I. We have a circular parallel plate capacitor. So this is not going to look circular because we're looking at it edge on, obviously, but circular parallel plate capacitor, and flowing current out this way, of course, I. And we're going to define our variable r, so the distance away from that, from the middle here, right, which is really not drawn at the middle, but you get the point. And the radius of the parallel plate capacitor is big R. Okay. The distance between the two plates is, sorry, D. Okay. And then we're going to hold on, let me get rid of this thing. Don't care, go away. Oh boy, okay. Just a second. Okay, so we'll define the positive direction in X. We may not need this, but we might as well define it. I like to put everything down. We're interested in a point P right here. Point P. We're going to figure out all the things about P, like what the electric field is, all kinds of stuff. Okay, so, and the distance away from this point here is, this little distance here is d prime. We're getting a little complicated here, but okay. Probably all we need right now. R is the variable, you know, that changes from going from the middle to the top, and we're just going to define that. I gotta move that up a little bit. That is going to be how far up P is. Okay. Anyway, what do we want to do for this thing? Well, a bunch of stuff. We'll first say that at time t equals 0, the capacitor is uncharged. Uncharged. Okay. We want to find a couple of things. So one, we want to find the electric field as a function of time at the point P. Okay, we of course want the whole vector, the magnitude and direction of that thing. We'd like to find the potential. Okay. At P. Given that, so given the potential at the right-hand plate is 0. Okay, so remember, you always have to define potentials as differences in potentials between 2 points. It doesn't make any sense if you don't do that. So on the right-hand side, we have V of t equals 0, or V equals 0 here. Oh, that's the left-hand side. Sorry. I can't tell my right from my left. V equals 0. Let me erase that little bit there. Okay. All right. All right, and we want to find the magnetic field at P. So that would be B of t. Okay, so why is everything a function of time? Well, the capacitor is charging, right? So we are not taking the case where the capacitor is fully charged and all the current stops. We're not dealing with that, right? We are right at the time where t equals 0, thing gets turned on, and we're right in the middle of charging the thing. So things are changing. The E field's changing because charge is building up. The B field's changing, etc. Okay, and we might look at the final energy near the end here. Sorry, total field energy we might get. Between the plates. May not have time for that. U of t. Okay. All right. Well, let's start. I don't really want to redraw that whole thing. So I'm going to put this diagram on the next page, and we'll just have to remember what we're doing. All right, hold on a second. All right, so now we're after our E field, right? That's what we're after now. Okay, so let me put that up here. We want, this is number 1, we want E of t. Okay, so here's our point P. Probably the easiest thing to do is to use Gauss's law. Okay, so let's see here. I'm just going to put the plate over here because it's too messy over there for me to draw on. And here's my point P. Okay, so what I'm going to do is make a little Gaussian pillbox. Goes right through that point. Okay, it doesn't really go through that point, but you see it's supposed to. Okay, and you can see, I hope you can see, that we have, oh, and we forgot to put the charges on the plates. We're going to have a negative Q on this one. So that means that the field is going to go this way, okay? So if we're going to draw the electric field, it would go like that, okay, and connect with the other point. Oh, I put the Q in the wrong place. Sorry, that's plus Q. And this one's got a minus Q. All right. And that's just convention. All right. All right. So now this is our E field. And the Gaussian pillbox, we want to say, has area like right here. This guy here has an area. So think of it as literally like a little pillbox. So if you looked at it to the side, it would look like, I guess, the same, but I can't really draw it very well. But it's a little box, okay? You know I can't draw anything 3D. I hope you get the picture. Sort of now imagine turning that on its side and putting it here. So there's a surface, which would be up here, which has surface area A, right? That's got A. All right. So Gauss's law tells us that the integral around this closed surface, this whole surface of E dot dA is going to be the Q enclosed over epsilon naught. And the first things first, I just like to figure out what is Q enclosed. All right, well, we didn't say this, we should have set this up a little better, but this plate has, of course, total charge, little q, but its charge density we can write as sigma is equal to Q over pi r squared, right? So that is the surface charge density. And remember that Q is not fixed, right? So little q is certainly not fixed. That is changing with time. As the charge gets pumped into the capacitor and charge builds up on the plate, the Q is changing with time. And so we can think about how does that work? Well, we know that Q at t equals 0, t equals 0 is equal to 0, and Q at some other time is just going to be IT. Just from dimensional analysis, okay? Pretty easy to figure that out. Okay, but anyway, just FYI, we can go over here and we can say, okay, what is the Q enclosed? Well, the Q enclosed has to be sigma, right, the charge density A over epsilon naught. And I'm not going to substitute all this stuff into it yet, but I'll just leave that. And so now we just have to worry about this. So think about it this way. The electric field that's you know, the dot product of the electric field along this side, right, with the area which points straight up, right, the outward pointing normal to that top part, it's perpendicular. E is this way, dA is this way, right, up this way, and that is just the dot product's going to get rid of that. Same with here. Over here there's no E field. And so all the surfaces except for that top surface, right, because we turn the box around so that top first surface is right here, is just not going to contribute. Furthermore, along that whole surface, E is constant. So that means I can pull E right out of the integral sign, and I end up with an integral dA. So I get on this side, I get E, right, no longer a vector because the dot product gets rid of that, and the integral dA, no longer a vector. And of course the integral dA is just A. So we end up with this equation that says EA is equal to sigma A over epsilon naught. All right, so again, easy to write down. We get E is equal to sigma over epsilon naught. Okay, now I can substitute all the Q and everything over in there. So let's go over here and do that. So we have E is sigma over epsilon naught, but we said sigma was, Q over pi r squared, then we have our epsilon naught, and then we said Q was IT, right, T over now pi r squared epsilon naught. Okay, so there's the magnitude of E, and of course we know it goes in the positive hex hat direction, right? Okay, so there's E, and as promised, it's changing with time. Okay. All right, so let's do the next part, which is finding the potential. So I'm gonna get another layer, be right there. All right, so now we're on number 2. We're gonna get the potential at that point. Get V of t. Okay. All right. So just to remind you how this what the potential is, it's always really delta V, but I'm just going to say V of t. Okay. And I'm going to say, just remind you that that's always the integral from, so not infinity, not minus infinity, from infinity into the point you're interested in, and that place is d prime for us, of the E dot dl, and dl is your path that you take along integrating in from infinity, x equal infinity, all the way into point P, which is at d prime. Okay, so this isn't too hard because we can split the integral up to the integral infinity to d, E dot dl, but outside of this plate, the E field 0. Of course, it's not true for a real capacitor, but for this capacitor, we're just not letting the field be anything outside. Okay, and so that whole integral is going to be 0. And then the next part is integrating in from d to d prime. And there we do have a field. And we're integrating along a line that just goes straight along the x-axis. Remember, the x-axis is x. Right, straight along the x-axis. And so this E dot dl, they're in this, same direction roughly. Don't worry about how you're integrating in from. In other words, that dot product doesn't really matter right now for signs. And then, so this is going to be equal to minus E, and then the integral dl from d to d prime. And of course, that's just minus E d prime minus d. And so that's just going to be E d minus d prime. Okay, so that's pretty simple. So V of t is E d minus d prime. And we can substitute what we know for E, which is IT over pi r squared epsilon naught d minus d prime. Okay, there's our potential. Okay. All right, on to the next. All righty, so let's go on to the next one. This is number 3, E of t. All right, for this one, let's just draw another picture here, a little bigger. Okay, here's our point P. And we want the magnetic field here, so I'm going to use Ampere's law, and let's remind us what that looks like. We've got to use the right one. So remember, it's B dot dl, right, along this closed curve C, which we haven't defined yet in our problem, is equal to mu 0 times the I enclosed plus mu 0 epsilon naught, the change in the electric flux through the surface bounded by that curve. Okay. All right, so now we got to figure out what curve to use. Well, remember the setup is, current coming in like this, current coming in like this, the electric field looks like this. So we expect that the magnetic field will be, by right-hand rule, right? We put our thumb in the direction of current, curl our fingers around. Hope you can see me curling my fingers around this way. So the B field's going to point straight out of my face. All right, so we expect that's its direction. So if we're going to make an Amperian loop, we should make a loop that kind of circles around like this with radius r, little r here, right? So this guy has a radius r. So this is our Amperian loop. And notice it goes right through our point P because we want the B field right there. Okay, all right. Now, using Ampere's law, you just don't end up doing it as many times as you do Gauss's law. So if this seems really foreign to you, go back and look at your text and do a few examples, very simple example problems of Ampere's law. It takes a little getting your head around. Okay, so let's calculate the integral first. Okay, this side. So we expect that the B field's going to point straight out towards me, okay, straight this way. And DL is just a little, so I'm going to draw Ampere loop over here on a different perspective. The DL is just a little tangent vector to the curve always. So that's DL. So it's always tangent to the curve, okay? And so you can see that DL is going to be in the same direction as B, right? So if you think of that loop as kind of like this, I can't draw it that way, but it looks, if you looked at it side on, right, it would look like this, like my hand, right? And if you turned it, it would look like a circle, right? Now it's head on, or side on. I just can't really draw it that way, so the way I've drawn it kind of looks like it's, you know, turned, but it's not. So the DL and the B are in the same direction, so the dot product is going to just give us, you know, BDL. And the B field, in fact, around the whole loop, because it's the same distance away from that center, is going to be the same. So I can pull it out of the integral. So I get B, the integral DL, around that loop. Oops, not a vector anymore, sorry. And that's just going to be B times 2 pi r, right, the circumference of that loop. Okay, so I have the integral. Now, on this side, right, I don't have any enclosed. I have no enclosed current, right? This is that situation we had before. So over here, I get 0 for this term, and I got to calculate this term. So I go plus mu 0 epsilon naught d, the change in the flux with time. All right, so I mean the electric flux, sorry. Here we go, so got to put that down. Okay, so if we figure out what the electric flux is, we're done. All right, so how do we get the electric flux? Well, it's just what we had before. The integral of E dot dA, but this is the flux just through this surface. And again, we can pick any surface we want, but you might as well pick an easy one in this case, right? So it's the surface bounded by that loop, that surface S. It's not closed surface, right? It is not a closed surface. That's has to be very clear about that. And if you can see, dA points outward like this, okay? And E also points in that direction, as we saw before, so the dot product just becomes EDA. And of course, along that whole surface, the value of the electric field is the same. So this becomes E, the integral SdA. And finally, this integral is just pi r squared, right, for the area. And we know what E is. E is, you know, IT over pi r squared epsilon naught, and then we have another pi r squared here, and so we end up with pi's cancel out, everything else kind of sticks around. We have IT, we have r squared over big R squared, we have epsilon naught, I think I got everything in there, and so now we just have to take the time derivative. And that's pretty easy to get this thing, because there's just time right here. So d phi dt, d phi e dt, sorry, e dt is equal to just I r squared over big R squared, and for epsilon naught. Okay, so now my B field will have my, so far I had 2 pi r b, and then I have mu 0 epsilon naught, and then my d phi dt, which is I r squared over epsilon naught r big R squared. This goes away, and so I end up with just I r squared over big R squared times mu naught, and so the whole B is mu 0, and then I have I, then I have R, some of the R's cancel, like there's an R here that cancels this guy, IR over 2 pi big R. Okay, and notice that B does not change with time, and its direction is out of the page. And that's, this doesn't change with time because of the very simple dependence on time that this had, that our flux had. Okay. So I think that's all we have time for. I hope this helps a little. Again, if there's little parts where you're like, I have no idea what she's doing, go back to your text and do some easy problems to try to figure out how this stuff works. This is a little bit complicated. Okay. See you later.